In my two lectures, I should like to give you some idea of notions, problems, and results in the theory of relational algebra. The task is not easy because the material is very comprehensive, and I shall have, for obvious reasons, be rather concise and skip over many important points. The development of relation algebra, its meaning and importance, should be properly viewed and discussed within a wider framework, within the framework of the general development of algebraic logic, which goes back to the half of the preceding century. Oh, maybe. Thank you very much. Start with the work of Boole. As you probably know, Boole was, here is a critical moment, I never know whether to say an English or an Irish logician, and if I say anything wrong, you know, that some people from one side or another may kill me, so I don't know what to say. It seems that he was an Englishman who was either born or at any rate brought up in Ireland and spent there most of his life. But I would not guarantee for the correctness of this information. George Boole, as you know, is the creator of a discipline which is known as theory of Boolean algebras. Its purpose was to develop, to provide an apparatus which would enable the scientists to develop a part of logic and the correspondent part of metalogic by means of algebraic methods. The part involved was the most elementary part of logic, known as sentential calculus. We know that the work of Boole really achieved this goal. Boolean algebras provide us such an apparatus for sentential calculus. Moreover, from the very beginning, they found applications and interpretations in other domains. They were treated as a kind of abstract algebras which have various models. Sentential calculus provides one model which could be called standard intended model for Boolean algebras. There are many other models in set theory, in topology, in various parts of analysis, even in such a theory as the theory of electric switchboards. From the point of view of logic, this was only the very beginning of what we now call algebraic logic. Because the part of logic involved is very elementary and is not sufficient, is far from being sufficient for serving as a base for the whole of mathematics. Clearly, the problem arose of founding a part of algebra, a theory of certain algebraic system, which would provide such an apparatus for more advanced parts of logic, and in particular for predicate logic, which, as we know now, is essentially the main part of logic which provides sufficient basis for the development of the whole of mathematics. Now, theory of relation algebra is a certain stage in this development. People started working on this theory very soon after the main papers of Boole appeared. The people who should be mentioned here is an Englishman, De Morgan, an American philosopher, Charles Peirce, a German, Ernest Schroeder. Theory of relation algebra is dealing already with a part of predicate calculus, of the calculus of quantifiers. A restricted part, it is true, and the restriction consists in particular in the fact that it deals only with binary predicates and with binary relations denoted by this predicate. So it is not the theory of arbitrary relations. Actually, the theory of relations of higher rank, Turner and so on, was never, to my knowledge, developed along the same lines as the theory of binary relations. On the other hand, I hope at the end of the second lecture I shall give you some idea how the theory of binary relations can be used to the development of the whole of mathematics. In the work of these people whom I mentioned, De Morgan, Peirce, and Schroeder, a calculus of relations was developed. Not a theory in a modern sense, but simply a machinery of proving and deriving laws involving binary relations. Only much later, in 1940, and later in the 40s of the present century, theory of relations was presented as a part of abstract algebra, as the theory of algebraic systems, of certain class of algebraic systems, and it became clear almost from the very beginning that, like the theory of Boolean algebra, it can be interpreted and has interesting and important models outside of logic proper, in particular in group theory. Instead of defining at once what I understand by relation algebra, I would like to give you an example, what is called in mathematics concrete example. Mathematicians use many terms in a very perverse way, in particular the word concrete. It is of course not concrete in any sense. To give you an example, what is called in mathematics concrete example. Mathematicians use many terms in a very perverse way, in particular the word concrete. It is of course not concrete in any sense in which we use this word in common language, is concrete in this sense that we don't deal there with arbitrary operations satisfying certain conditions, but in operations of a well-defined set theoretical character. So let's consider an arbitrary set A, of which we assume that it is not empty. By a binary relation on a binary relation R on A, we understand, in set theory normally, every set of ordered pairs. Everything which has a graph in a normal two-axial coordinate system, in case A is the set of real numbers. But, as I say, A can be a set of an arbitrary character. If, as it is normally done, by A cross A, we denote the Cartesian square of A. This means the set of all ordered pairs whose members are elements of A, then we can say that a binary relation R is an arbitrary subset of the Cartesian square. So we know what is a binary relation on a set A. Now we can perform on this relation various operations. Since, for instance, R and S, another relation, are sets, we can treat them as sets. We can perform on them Boolean operations, such we can take union of two relations, intersection or common part of two relations. Given any relation R, we can form the difference between A cross A and R, which we denote simply by, in this way, putting A here, and we call it the complement of R relatively to A. If A is fixed, we simply omit A here and here. So we have a unary operation on relations. Then we have also a certain operations on relations which do not apply to arbitrary sets, which are characteristic for relations, for binary relations, and have no clear meaning when applied to sets that are not relations. Such is the operation of relative product or composition of two relations, which we denote by means of strokes, following Principia Mathematica. What do we understand by this? This again a certain set of ordered pairs. If I use normal set theoretical terminology, I could write here the set of pairs x, y, where x and y belong to A. So as you see, this operation also depends on A. But A is assumed to be fixed, no? And let me use normal logical symbolism. There exists a G belonging to A, such that XG is in R and Gy is in S. So this is the relation, the operation of relative multiplication of two relations. We know many examples of this operation. It's a very important operation well, in common language even. And the evidence is provided by the fact that for the relations, for all the relative products of certain relations whose names exist in common language, special terms were introduced denoting this product. To give you an example, and most examples which are given in this connection are from the domain of family relations. Let's take the relation of being a son-in-law. So let T be the relation of being a son-in-law. If I write xy or xy belongs to T, I read this: X is a son-in-law of Y. And now what is the common definition of this relation is this: to say that X is a son-in-law of Y means that they exist as V, such that X is husband of V, and V is daughter of Y. So that T is defined in this way. T holds between X and Y if they is as V, so that X is husband of V and V is daughter of Y. Therefore, according to our definition, T is the direct product of H and V. Relation of being son-in-law is a direct product of the relation of being a husband and the relation of being a daughter. You can give many examples, as many as you wish. In particular, there are interesting cases when H and D is the same relation. This means cases when T is the direct product, a relative product of two relations R, that means relative square of R, sometimes denoted in this way. For instance, if R is the relation of being a child, then R square is the relation of being a grandchild, because a grandchild means a child of a child. It is also a good field for exercises. For instance, you can ask the following question: is the relation of being a grandson a relative square of the relation of being a son? And then you see, of course, at once that the answer is, I expect you help and you don't give me. No. Because a son of a daughter is also a grandson. So you see, X is a grandson of Y doesn't imply that X is a son of V and V is a son of Y. Another example of a relation, of an operation of on relations, a much simpler example is the unary operation of forming a converse of a relation. Let me use here not the symbol converse, but the symbol more often used in mathematics, R to the power minus 1. The converse of a relation R. Well, this is the relation obtained from R by interchanging the terms in each pair. xy belongs to R minus 1 if and only if yx belongs to R. For instance, if R is the relation of being a child, then R minus 1 is the relation of being a parent. No. But if R is the relation of being a son, then R minus 1 is again not the relation of being a father, because it could be also that for Y we take not the father of X, but the mother of X. And we